Hello, my name is Ryan Passage, and I'll be presenting a paper titled An Experimental Security Analysis of an Industrial Robot Controller. This is being presented for the CS6263 Introduction to Cyber-Physical Systems Security at Georgia Tech during the summer 2019 semester. This paper was originally presented at the 2017 IEEE Symposium on Security and Privacy. Its authors are David Quarta, Marcello Pogliani, Mario Polino, Andrea Maria Zenchedin, and Stefano Zanero from Politecnico di Milano in Italy, and Federico Maggi from Trend Micro Incorporated. So here's the agenda for the presentation. We'll start with a brief introduction, then we'll look at context and key observations made by the authors. We will look at attacker models, their goals, access requirements, and capabilities. And then we'll look a little bit at industrial robot architectures as far as what their purpose is for, the components that make up an industrial robot, and their functionality. We'll look at attacking industrial robots, where the authors outline several different ways to attack this platform. Then we'll move into a case study on the ABB Robotics IRB 140 model. We'll look at security measures and recommendations following that case study, and then wrap up with summary and conclusions. Okay, so just a brief introduction on industrial robots for maybe those who aren't familiar with manufacturing and industrial environments. Industrial robots are mechanical multi-axis arms, as you see in the picture here to the right, and they're used, of course, typically in manufacturing and automation. There's some numbers here that kind of help set the stage and scope for why it's so critical that we secure these platforms. Like in 2018, there were an estimated 1.3 million industrial robots in use at factories around the world, and the market value for all these systems put together is estimated to be around $32 billion. So those are big numbers, and we want to make sure we keep those numbers and those robots and platforms safe. Of course, as robots have grown in sophistication, as we've moved from the old style robots that really were just performing single function and weren't connected to anything, to these newer, more automated, more connected systems, that has increased the attack surfaces and, of course, exposed us to new risks, including safety, impacts to productivity and downtime, effects to market reputation, and theft of intellectual property as well. So the authors provided some context for why they did their study by taking a look at modern industrial robot cybersecurity and making three key observations about its current state and how they were able to move forward based on those observations to conduct their study. One of the first observations that the authors make is that our robots are increasingly connected. This connectivity is resulting in increased exposure, of course, to cyber attacks. As you add more devices to networks, those devices, if they're not kept up to date and proper precautions aren't put in place, are, of course, targets. And these robots, as I mentioned before, decades ago, were designed to be isolated. Networking wasn't really a consideration. But today's industrial robots are exposed to network connectivity, including corporate networks, where of course we know we have malware challenges and other issues there, and the internet when looking at IoT. So the connectivity serves two primary purposes. Of course, it's programming and maintenance, but it does, of course, increase a robot's exposure to threats. So, of course, one thing that's always top of mind in manufacturing environments is operator safety, and this is a real concern when we talk about operators working in close proximity to robots. And of course, traditionally, they were designed to operate in workspaces that had some kind of physical barrier, whether it's a cage or a wall, preventing the operator from coming too close. However, vendors are starting to introduce new models of what they're calling cobots, collaborative robots, which are actually designed to share the same working space as humans. You can see where this is going from a safety perspective. Compounding this risk is where we're starting to move some of our control of safety features from a hardwire, fail-safe wire or switch that can be cut and killed to immediately power down a robot and stop it in its tracks, or moving those features into software. And the implementation of those features in software opens up the potential impact of an attack to operator safety. So in an attempt to better understand what the awareness is out there in the robot manufacturing user space of security and its risks and impacts, the authors conducted a survey. They sent 50 what they're calling domain experts a poll, a survey, and what you see here on the right is just a snapshot of a part of the results of the survey, and some numbers that they include here, where they got about a 40% response rate. 30% of those responders found the default safety settings on their robots to be too limiting, which means that 60% said that they had customized those security settings. Now, whether they customize them to the good or to the bad, it's hard to say, but if they found them too limiting, chances are pretty good those customizations included disabling some security safety settings. 28% did not enforce any access control policies on robot controllers. Remember, these are increasingly more network connected. 30% had robots accessible from the internet. And 76% have never performed a professional cybersecurity assessment, which is a pretty big number there. So overall, the big takeaway here is that more than 50% did not consider cyber attacks a realistic threat. And these are people that are using and managing and installing these robots on a daily basis, and relying on them to enhance their business, but also to be a reliable presence on their manufacturing plant floor, and one that they can trust because they trust how it's been programmed, not necessarily how it's been secured. So their awareness of security risks is scarce by the results of the survey, as you can see. Okay, so now we're going to look at the attacker models that the authors established, really where they looked at 3 criteria for these attackers: their goals, the level of access required to carry out successful attacks, and the capabilities that the attackers have, really as it relates to the amount of information that they're able to get a hold of, which we'll see is quite substantial for these robot platforms. So what are some of the attackers' goals and some of the threat scenarios that are at risk here? And the authors say that attackers simply want to obtain control of industrial robots to carry out attacks because they interact with the physical world. So that opens up some additional options that maybe aren't available on a run-of-the-mill corporate network, or if they're an attacker who's just trying to phish someone's email account. So looking at some of those threat scenarios and possible risks, those can include, of course, physical damage, where the attacker can cause damage to the machinery or cause injury to the operators. Production plant halting, where if the damage is substantial, production at a facility can be halted for quite some time, and the longer the production is halted, usually the more costlier the incident is. And also unauthorized access. Maybe they're not looking to damage something, maybe they're looking for sensitive data. Could be source code, production and operational data and schematics, or intellectual property. How can attackers access the robots that they're looking to exploit? And the authors identify 3 main types of access level that allows these attacks. The first being the network attacker. This is actually not internet-based like you might think. This is attacks that are perpetrated by insider threats. So a lot of today's industrial networks may be connected directly to the corporate network, hopefully with some firewalls in place, but that's part of securing the environment. And if those aren't there, then the industrial networks are opened up to threats from malware and other corporate type risk. Another access level is remote exposure. This is talking about robots connected to the internet, which is becoming more and more common. And you can use IoT search indexes and search engines like Shodan and ZoomEye to discover some exposed robots, and just like you and I can run searches, so can attackers. So if those robots that are exposed to the internet have been indexed by these services, they are now available for attackers to discover and to try and exploit. And then we have the physical attacker, which really is the robot operator themselves. For example, a disgruntled worker. This can be the simplest and most common form of physical attacker because, of course, they have such easy access to the robot itself. So all it takes is a disgruntled worker who knows what he's doing with that teach pendant to put in a logic bomb or some other kind of vulnerability or weakness into the robot that can cause some serious damage. So the authors actually say because of that easy access, even a casual physical attacker is more powerful than a skilled network attacker. So based on those access levels, the authors say we can profile attack vectors as being either physical or networked. And as I said, they found the most likely source for physical attacks to be a company insider, while, as you might imagine, the network attacks have a much broader surface, and they're much more attractive to your larger set of cyber criminals that are out there. So one thing the authors also comment on, and this is relevant if you watch the news, is nation-state level attackers. So although threats come from all sources, insiders, script kiddies that are just kind of taking pot shots based on showdown search results, and of course your true cyber criminals, there's nation-state actors out there that operate on a totally different level. They're able to target assets from almost anywhere through almost all access levels, and have a deep knowledge of the architecture and the weaknesses of these platforms. And of course, if we're talking about nation states, we're saying there's deep pockets involved. And for most organizations, realistically speaking, they don't have the resources to compete with their security measures at a level that really provides accurate and sufficient protection from a determined nation state attacker. So what gives attackers their capabilities? And it turns out pretty often it's access to information. And so as defenders, people who are securing these environments, we should assume that attackers are familiar with their target robot's infrastructure and design, and that they've done their homework. A lot of times this information that the attackers are using is coming directly from the vendors themselves. The vendors will often make resources public, such as full system documentation, and even in some cases including source code. They'll make downloads of their operating system software and firmware available, which of course can be reverse engineered and studied. And in some cases, for teaching purposes, they'll also make simulation environments available, which attackers can use for vulnerability development and testing. And one example that's used in the paper here is ABB's Robot Studio Suite that the authors are citing, which actually provides full simulation environment, including a code library. And this sim and this code library that they're supplying is the same code that's running on their production controllers. So if an attacker is able to download this sim, play around with it, and find a vulnerability, they can feel relatively confident that that vulnerability also will work on a production system. One control that can be put in place that the authors mention is that vendors who only supply this type of information to customers with active support contracts, meaning they've bought a robot, they're paying for a support contract, usually annually. If they limit the availability of this information to only those customers, it can help to slow the development of vulnerabilities because access to that information is limited and harder to come by. Okay, so we're going to take a real quick tour through the industrial robot architecture, really what their purpose is, again, what their components are, and the functionality that they provide. So just a general overview of robots. They are extensively standardized and similar across all vendors. They have high complexity in their controllers because they're expected to have a multi-purpose nature. And as I said earlier in the introduction, typically an industrial robot is really just an arm that has two or more joints terminated by some kind of tool which they call an end effector. This can be pliers, a laser, whatever that allows them to interact with their environment. Now each robot has a controller, which is the brain of the system, like a CPU. These controllers are connected. They have a lot of interconnected electrical and computer systems, and they're usually enclosed in a chassis to provide protection from the physical environment, because some of those manufacturing environments are kind of harsh, but also just to hide the controller out of the way. Controllers themselves are designed for efficiency, to provide complex motion and interaction with human operators. And they typically all share a common software architecture. And in a lot of cases, the interfaces to these controllers run an embedded version of Windows CE. And of course, robots are also designed to be interacted with by humans. They're in charge of monitoring, starting, and stopping the operations of a robot. And this is typically done through a process called human-robot interaction, and done via user interface. And one example of this, a very common example, is the Teach Pendant, which is a handheld device that's connected to the controller. It allows the human operator to monitor, adjust the robot. It's also used for programming, and allows the human to issue commands directly to the robot, telling it what to do, where to move, and so on. Okay, so now that we understand what a robot is and how it works, we're going to look at how they can be attacked, and look at, in particular, 3 specific attack scenarios and how those can be executed. One attack type is the control loop alteration. So this attack works at the servo level, so we're talking about the motors and the servos that control the robot's movement. And in particular, attackers are able to access configuration files, usually because of user authentication weaknesses, where they're allowed to modify its movement and configuration parameters. And so what can happen is this attack can violate both functional and safety requirements. So there's a couple examples here: the robot arm and workpiece configuration tampering. So again, just talking about the configuration settings of the robot and the tool that's on the end of the robot. And then also the safety limits tampering, which can be speed, movement direction, and what can cause harm to the human operator. So second attack type is the user-perceived robot state alteration, which is really just kind of a fake out for the operator. Of course, operators use robots through their human interfaces, those Teach Pendants and other screens. And in order to use a robot effectively, the operator needs to be able to trust what they're seeing on the screen, the data that's being supplied from the controller, and the commands that are being issued and then acknowledged by the robot. Some of these conditions and functionalities are controlled by software now, and so an attacker can actually perform a UI modification attack, which can fool an operator into performing an incorrect evaluation of the robot's status, issue bad commands, and cause it to create damage or physical harm, or whatever the scenario may be that the attacker is aiming for. So the third major attack that the authors explore is the robot state alteration, which builds off of the previous UI alteration attack that we just looked at. This is both an attack on the perceived state displayed to the operator, but also the robot's true state, which you can imagine is very dangerous. So a couple examples are the motor state alteration, where the motor state is changed silently in software from manual to automatic, which would cause it to execute programming steps, maybe if there's an operator nearby, which of course is a safety risk. And then software or wireless safety features is another type of this attack, where some features that are implemented in software really should be done in hardware, like the e-stop, emergency stop button, which opens them up to UI modification attacks as well. The operator thinks that the software e-stop button is going to work when in fact maybe it's been disabled. So after discussing the different attack types, or some of them anyways, the authors then went into a case study on a security analysis and really a vulnerability analysis that they did on a model robot, which is just kind of a standard model, very similar to what's used across the industry. In this case, it's the ABB Robotics IRB 140. As I said, they did their analysis on an ABB IRB 140 robot, very standard design in manufacturing and industrial robots. This robot is equipped with a widely deployed controller. It's very common, and its Teach Pendant is Windows CE based, which is also very common. The total cost for this robot, including all the accessories, cages, cabling, everything, was around $75,000. So if you consider a successful attack in a factory full of these robots, it can be quite costly, all the damage that can be done. So looking at this robot, some of the attack surfaces that the authors talked about were the components involved, including the Teach Pendant, the main computer, Axis computer, which controls the servo motor, as well as its panel board, which also controls some of the safety critical conditions and the robot's response to those. And then, of course, the network and physical ports being Ethernet and USB. So they also discussed design risks related to these robots, such as exposed network services like FTP and other APIs for management, and boot processes that automatically trust firmware that they pull from an FTP server without doing too many code signing checks or any at all. So after looking at those components and those vulnerabilities, the authors crafted some attacks, and they were able to successfully exploit the IRB-140's controller. The path to exploitation that you see there near the bottom is a quick summary of what they were able to do, and it included some vulnerabilities such as abusing static credentials, using those credentials to authenticate with the system and then disable further authentication requirements, of course uploading that untrusted payload that the robot then installed and booted from, and then they were able to give themselves persistent access because of a switch included in that boot payload that they had uploaded. So all in all, they were able to find several vulnerabilities, exploit them, and gain control of the robot's controller. So then they followed up with a review of the security measures and some of their recommendations, which really just kind of takes a broad view of these vulnerabilities that they discovered, and then what maybe can be done as security practitioners to improve the security of these robots. And when we're looking at designing secure architecture for these robots, it's already a difficult task, but for these robots, the situation's even harder because of critical operational concerns, such as being able to provide timely security updates, robots that are expected to have very long lifetimes, meaning manufacturers have to support them for a very long time. Vulnerabilities that may never even be patched, which they refer to as forever day vulnerabilities, kind of the opposite of a 0-day. And then, of course, customers don't want to install patches anyways because that creates downtime, and so they just won't do it. And then, of course, the big one always at the top of the list is operator safety. So without going too deep into some of the recommendations they made, they did identify some areas that can be addressed, including human interaction, attack detection and system hardening, and then what can be done during the software design and development phase of the robot controller. And they made some recommendations, including such things as attack detection, secure software development lifecycle, and so on. And if you take all of these recommendations and apply them, we can expect to see the security of an industrial robot improved. So looking at the conclusions here, we can see how the authors were able to explore challenges and impacts related to industrial robot infrastructure and providing the security there. They were then able to model successful attacks against vulnerabilities, including showing how they did that to be successful as attackers. And I think what we got out of this was a very good, very thorough example of how risky unsecured robots can be in their environments, because we're looking at risks like financial loss, productivity loss, and of course human injury or even loss of life, which is very realistic. It happens. And all these are, of course, great threats and really need to be taken seriously by security practitioners who are trying to work in an environment such as manufacturing, which is very much get it done, not looking for downtime and creating new obstacles to productivity. But at the same time, research like this is important. It can be shown to these people who maybe aren't interested, to really kind of outline the risks and make them seem real enough to hopefully convince them that these are serious environments. They need to be secured, and that can actually be done in a way that enhances their production systems. Thank you very much for your time and attention.